Thank you very much. My name is Satoshi Miyazaki from National Astronomical Observatory of Japan. Today, I'm going to talk about our current project, which we call Hyper Suprime-Cam. But before I start my instrumentation talk, let me start from this slide. Our interest is that how does the universe expand? And traditionally, the universe expansion is supposed to be deaccelerated, just like the thrown ball comes back to the Earth. But the astronomer found that rather acceleration rather than the deacceleration. So this is very surprising and something really new. And many people are interested in that. And that's why they had 3 astronomers leading 2 projects awarded the 2011 Nobel Prize in Physics. What did they actually observe? What they actually observed was the expansion history of the universe. These 3 curves is a representative model prediction of expansion history of the universe. And traditionally, the blue line is a traditional curve, which is deaccelerated. And if you introduce the cosmological constant, the acceleration was predicted. And what they observe is actually looking back to the past. And this is expansion, the view of looking back. And the vertical axis is the relative size of the universe, which we call AT. And AT is simply related with the redshift from this equation. And let's say we observe that the redshift 1.0, that is a half size of the universe. And when we look back, the actual distance, I mean the time, look back time, depends on the cosmological model. And let's see why it doesn't go. So the actual look back time depends on the cosmological model like this. And if you have a standard candle, which we know the maximum brightness, it can be used as the distance measures. And what they actually observed was the redshift versus magnitude. And this bold line is a prediction from the standard, most traditional models. But most of the supernovae were fainter than expected. And this is the evidence of the existence of the cosmological parameter. So this is very useful. And we are very interested in this nature of the cosmological constant, which is generalized to the dark energy. And we really want to observe in some independent way. And what we're going to use is the evolution of the large-scale structure, which is shown in this movie. The large-scale structure of the universe is determined by, of course, the gravity, and also related with the expansion of the universe itself. The growth of the density fluctuation, is defined as a deviation from the mean density. This delta is in linear regime. The evolution is governed by this simple 2-order differential equations. This is very familiar for the first year or second year physics course student, which is forced oscillation. So this term, the first order derivative, of the time is friction time. And if you don't have this friction term, the evolution of delta is exponential. So in a sense, this expansion of the universe itself suppress the growth of the exponential evolution. So if we have an expansion, this growth rate is power to the time. So evolution, I said that evolution of large scale structure is governed by gravity theory and expansion history of the time. And this expansion of history of the time is very, very interesting object because they said it is accelerated. And what we're going to observe is the universe and try to map the universe to see this evolution of the large-scale structures. And this might, dark energy or cosmological constant might, make this expansion accelerated. And so from this observing, we are trying to understand the nature of the mysterious energy. So our mission is surveying the distant and faint objects over the very, very wide field. So we need the large telescope with a wide field camera. So this type of small telescope is not enough, and we use somehow larger telescope like Subaru. Subaru has 3-4C, and one of the prominent features is this prime focus on this 8.2 meter telescope. The Subaru primary mirror is controlled by the 221 actuators, and this actuator is actually controlled by the static lookup table, which is created through the mirror analysis processing, and no real-time wavefront sensing measurement is necessary, which means that the telescope itself is very, very stable and ideal for the wide-field optical camera. So we built a camera nearly 10 years ago or more with the University of Tokyo group led by Okamura sensei, and which we named the Suprime-Cam. That's adopt the 10 MIT Lincoln Lab CCDs, and the field size is 30 arc minutes. That was really uniquely wide field on 8 to 10 meter class telescope. So compared with HSC, that was, the size, the field size is already like 100 times in area. And what we're going to try to build is a much wider camera in order to make the survey speed faster. So here is a cross-sectional view of the camera and how it looks like. Because it's a camera, we have a lens, filters, shutters, and CCDs. And the height is like 3 meters tall, and the weight is, including the filter exchanger system, is like 3.2 tons, and nearly gigapixel. So this is more like a schematic diagram to show you the system units of our Hyper Suprime-Cam. So here we have a wide field correctors. The camera is installed inside this prime focus unit. And the prime focus unit is sitting on this telescope inner hub. And the entire camera system is controlled by this hexapod called the Stewart platform. So the camera itself is hooked from the top, and the entire system is aligned to the M1 axis. And we have an incident rotator here, and the camera, only camera rotates, although the wide field corrector stays the same. So this configuration is basically the same as the Suprime-Cam, although this we introduce larger wide field correctors and camera. And because the size is limited here, we don't have any space for the filter exchanger. So we decided to mount the filter exchanger outside of this prime focus unit, just like this. And this greenish section shows you the filter exchanger. When we install the filter, this portion is flapped down, and the filter is inserted and extracted. And we have 3 slots on each side, so the 6 filters are installed at one time. So here is the error budget distribution of our image in I-band, and the total budget is 0.37 arcsecond FWHM, which is very similar to, I think, the LSSD is trying to realize, and which is composed of the diffractions and mirrors and tracking errors, or something like this level. Of course, the diffraction is mostly negligible in this optical band. And we allocated the 0.2 arcsecond to the wide field correctors. This is all FWHM. And 0.16 arcsecond is allocated for the optic misalignment, I mean the collimation error. And also, there is no negligible charge diffusion, which I talk about this a little bit later. The optics misalignment, the major component is cubic coupling between the telescope and the HSC, because there is some unrepeatable error when we mount the camera on the telescope, and the cubic coupling accuracy is very crucial. And also the instrument rotator bearing is one of the critical components. And also the CCD Co-planarity must be taken into account. So those are all measures. And adding up with another minor components, we have 0.156 or something like that errors for this optics misalignment. Here, we showed how our HSC optics looks like. So here's a 8-meter primary, and we have correctors. The zoom view is shown here. So we have a 1 mirror plus the 7-element correctors shown like this. And the feature of the corrector is that we adopt the atmospheric dispersion corrector, because this is not only for the camera, but we use this corrector for the future spectrograph, which is being built by University of Tokyo, and other many international collaborations. So here's a zoom up of the wide field corrector, and basically this configuration is all the same as the previous version of our correctors. This is the 3 basic triplet, wing triplet, plus lateral shift correctors, and there's 2 pairs of the glasses which compensate the chromatic aberration introduced by lateral shift ADC. And there are a couple of aspheres introduced, and some of them are convex aspheric. And this is built by actually Canon, and here they have a contact type freeform measurement system, and that allows us to introduce the convex aspheric. This is the lateral shift ADC is invented by the former Canon engineer, Mr. Takeshi, Dr. Takeshi, sorry. And this is basically, generate the chromatic aberration intentionally. And when we shift the unit, the chief ray goes straight, because the index is mostly matched with the chief ray. Although for the shorter blue ray, the ray transparent from the low index to the high index material, we have a refraction from this direction, and the red is the opposite. So what we're going to have is, the spread of the rays, And if we have a original dispersion caused by the atmospheric dispersion, the ray will converge like this. But as I said, the chromatic aberration is intentionally introduced here. Some compensator is required, which is actually sitting right here after this lateral shift ADC. So the benefit of the ADC is clearly demonstrated on this figure. Without ADC, this is a sort of a encircled energy diagram for the horizontal axis radius. And when we make the ADC engage at the proper position for the encircled energy is rapidly going up. Whereas if it's not in the proper position, the smear, image smear is very, very large. And this is, compared with the traditional rotation prism, we only need 2 elements, and this surface also can be used for the regular lens system to suppress the aberration. So this is a very, very key feature of Suprime-Cam and the Hyper Suprime-Cam. So when we assemble the lens itself is installed on the rim lens barrel made of ceramic. It's called sphalerite, and those are stuck them and eventually build up like this. And we measure the wave front error and the estimated worst performance over the field of view, including everything. I mean, the manufacturing and the figuring error is better than 0.18, which met the specification. So the CCD is built by Hamamatsu, and we have long-term collaboration initiated originally by Ie-san. And finally, we have a very nice 2K, 4K fully depleted LVL type CCDs in 2008. And this is a very conventional size, 2K, 4K, 15 micron, 200 micron sec. And we fed the signal back from the back using this ping read arrays. And the CCD's flatness is secured by 10 micron flatness is achieved in some cases, but some cases the corner is a little bit worse. But on average, the flatness is mostly secured. And thanks to the thickness, we have a very high QE in the red band, and more like nearly 40% at 1 micron at minus 100 degrees C. The charge diffusion is measured at RAB, and it is expected 1D sigma this diffusion is nearly half of the pixel, like a 7 micron. But we can improve this, make this diffusion smaller by applying the higher voltage on the backside. But there is a practical limit. So we compromise at the 7 micron. So when we assemble all together, the camera focal plane looks like this. And there's a readout electronics back of the cold plate. The cold plate is made of silicon carbide. And this is a height variation of the camera. It's like, it's kind of hard to see from this picture, so let me show you the radial profile. From horizontal axis shows the distance from the center to the edge, and vertical is axis shows you the height. And each bar corresponds to each CCD, showing you the minimum and the peak and the valley. Because our focal plane is not totally flat, we sort of arrange the CCD so that it's follow this best fit image plane. And that's why we have some bump right here. This is intentional. And so this is from 0 to 50 microns, so nearly like peak to valley is a 30 micron, 35 micron. And This can be translated into the RMS by dividing roughly by square root 2. Sorry, this is. And this corresponds to the delta FWHM for the impact on the image quality is 0.077 arcsecond. Here is a cooler. This is Fuji Electric 45 watt at minus 100. And someone, you asked about the vibration, but we measured it using the laser displacement meter, and that was like a 0.2.4 micron at the focal plane, so it's very negligible. So if you mechanically connect this, chord head to the focal plane with some flexure heat path, that should be fine. And we also have 20 liter per minute ion pump to feed out all the outgassing from the electronics. And that's the lifetime, expected lifetime of ion pump is like 2 or 3 years, so that's long enough. So assembled together, the camera looks like this, and we have a shutter just beneath the code duer. And the camera itself is now docking onto this prime focus unit, and the lens is already there. So mounted on the telescope, the camera looks like this, and we are ready for observing. So here I show you some of the results from our performance verification test. This is the expected PSF if we don't have any seeing. But combined with the 0.4 arcsecond seeing, it looks like this. And we will see how different the actual world is different from the ideal world. Here, after the sort of couple of adjustments run, we finally have a very, very nice image over the field. This shows you the stellar size over the field. This is 1.5 degree, and the center is 0.43, and the edge is 0.47, and it's nearly better than 0.45 arcsecond thing. It's realized over the field of view. And this is a radial profile of this stellar size, and here is the edge of the field, 45 minute, and 0.4 is right here. So expected from the optics ray tracing, combined with the 0.41 arcsecond seeing, is something like this, which follows the actual the image data quite nicely. And if you have some displacement of the focus shift, if you go farther from the telescope, I mean the primary, by 50 microsecond, the greenish point is resolved. And minus 50 toward the 50 micron toward M1 is the red dot is the prediction. So it's I think the CCD Co-planarity is less than 50 micron because it's not go beyond 50 micron from this figure, which is consistent with our lab measurement. So we are interested in ellipticity because we are interested in weak lensing. And observe the ellipticity map looks like this. And expected from the perfect system, perfectly aligned system, and manufactured system is somehow look like this. So this is the result of the prediction, the calculation. And the radial pattern looks similar, but the amplitude is quite different. When we displace the focus position, this radial pattern is more visible on the plus side, and minus side is not the radial pattern. And this is also the design optics. So when I plot the radial diagram again, this is a prediction, but the actual ellipticity that we observed at 0.4 arcsecond seeing is something like this. So something is smears the image. CCD non-co-planarity, maybe not, because we have a radial growth. Tracking or guide error, no, maybe. the counting statistics, of course, not. Atmosphere may explain this central bias. So what we consider next is figuring and assembly errors, which is actually measured when we assemble the wide field correctors. And that, if we take those errors into account when we make ray tracing, we have some like more smeared image is expected. And actually, when we overplot the plus 50 micron things, this is going higher, like twice, and close to this actual values. So not all the same, everything is not explained, but most of them may be explained by the actual assembly and measured error. But the slight focus displacement causes image smear. So most of the smear could be explained by the optics misalignment, but more data needed to characterize the instrument PSF. And we have another 5 or 7 engineering night, and we hope we can get more data to fully understand our PSF. So the survey began last February, actually, and this is a sort of a stepping pattern to pave the sky. And this here is a 1.5 degree circle is plotted here. And we actually observe. In 2 hours, we can cover like 20 square degrees. And this night was very nice night. And we have an average seeing of like a 0.5 arc second over our entire field of view. It was amazing. And when you look at the sample image, it's something like this. We have a lot of galaxies. And the galaxy is not our final object because the galaxy itself is not a representative of the underlying mass distribution. And because many, we have many dark matter. So we are trying to estimate the distribution of the dark matter more directly using the gravitational lensing. If you have a very, very massive object in between the distant faint galaxies and between us, we have this kind of coherent shear pattern. And if you have a lot of, statistically, we look for the shear pattern, and we can create the dark matter map like this. And as I said, understanding the PSF is crucial to do this business. So we actually created the dark matter maps from that 20 square degree image, and this is shown is the result. And then you have a whole bunch of peaks, which we suppose the cluster of the galaxies, dark matter concentration candidate. And when we look at this, the highest signal image and zoom in, here we have a very beautiful cluster of galaxies with a lot of arcs, which indicate that the cluster is massive. So using weak lensing, we are able to measure the total mass of the cluster of galaxies more accurately. And mass-selected cluster catalog is primarily crucial for cosmology and also useful for astronomy. And because the cluster mass function is very, very sensitive to these cosmological parameters. So I think I'm running out of time. Let me skip this cosmic shear thing and go into this conclusion. We actually submitted a proposal a year ago with Princeton collaborators and Taiwanese collaborators and all Japan collaborators. We have 166 COI, and we are trying to observe the 1,400 square degrees in the wide area, and that was 20. The I showed before was 20 square degrees. It's only like a small fraction of the entire survey area. But that's a part of this survey, actually. And we have a very good start. And compare with other surveys, ours is deeper and sharper. Compared, for example, the DES is also running parallel. But our feature is the depth and the image quality is a little bit better than the other. And following us, of course, there's a future project called Euclid and SST, but those are not begun by 2020s. So we really want to do something new before they actually start the project. Okay, this is also skipped. So my conclusion is that we have successfully built the Hyper Suprime-Cam, and that's a 3x3 meter tall, 1 gigapixel digital camera for 8.2 meters Subaru Telescope. And the 5-year survey just began this spring. And this is open for general users. And thank you very much. And this is our colleagues. They're all young, and we are I'm very happy to work with them through this maybe 5 or 6 years project. Thank you very much.